First review, the main point of yesterday's discussion. Yesterday's discussion was about the gauge fields in 2 + 1 dimensions, their deep connection to the superfluid phase, and to the Nambu-Goldstone boson, the abelian Nambu-Goldstone boson. So we discussed two models which turned out to be dual in the deep infrared, in the sense that if you probe their physics near the phase transition, then they appear to be the same, despite the fact that the Lagrangian is totally different, with different fields, completely different ingredients, but at long distances they turn out to be the same. So one model was the O2 model, which two phases at large negative m squared, the phi field condenses, spontaneously breaking the O2 symmetry, where the O2 symmetry acts on phi by just ordinary rotations of phi. And so at large negative m squared, there is a circle of vacua, phi condenses, the O2 symmetry is broken, so this vector has a vev, and vacuum, and their phase transition is given by the O2 conformal field theory, which is an abstract entity with some scaling dimensions. Then we discussed the gauge field theory, where there is a gauge field that's coupled to a complex scalar of charge 1, a single complex scalar of charge 1. This model also has a U1 global symmetry, which is what? Anyway, somebody remembers? The magnetic... Yeah, the magnetic symmetry. So there is a U1 magnetic symmetry of U1 magnetic symmetry is a slightly exotic symmetry because no local operators that are made out of the phi twiddle or f mu have any charge under this symmetry, but instead we have magnetic monopole operators as they're called. And in the phase where m twiddle squared is huge and we integrate out phi twiddle, we just have a free gauge field. It's a Coulomb phase, and in the Coulomb phase, the monopole operator has an expectation value. This is the dual of this phase. So instead of phi, an expectation value here, the monopole has an expectation value, and we have a circle of vacua. We discussed that in this phase, electric probe particles have a Coulomb force, and so on. And if we were to break the symmetry slightly by adding monopoles to the Lagrangian, they would be confined. Then there is the phase where there is a Higgs mechanism and there is a single vacuum. And it's described, the phase transition is the same, and there is a duality where m squared is going to minus m twiddle squared. Okay, so that's the... now, this example is very, very nice, but in some sense, conceptually, it doesn't bring us very far. Because even though we invested this huge effort in studying gauge fields and understanding what they do, in the end, you get something that's equivalent to the ordinary O2 model. So you could ask, why do we need this whole thing? What I'm going to show, and another comment is that phase transition in this model is an ordinary Landau-Ginzburg phase transition. The way I define Landau-Ginzburg phase transitions is that these are phase transitions which have an order parameter. So there is a broken phase, there is an unbroken phase. It's a standard thing in statistical physics. And Landau-Ginzburg phase transitions are those that can be described by scalar fields, and this indeed can be described with just scalar fields. You don't need gauge fields, and that's the way to do it. So today I'll show you something much more surprising that people discovered much more recently. In condensed matter, it's called the Néel-VBS model. Where VBS stands for valence, bond, solid. This sounds somewhat of a mysterious thing, but it has a very nice field theory description, which is an extremely close cousin of this. And it displays something that many of you, I'm sure, have never seen before. It displays a phase transition which cannot be explained with scalar fields. And there cannot be a dual with just scalar fields. That's the simplest example, I think, of a model or of a system that is beyond the Landau-Ginzburg paradigm. And this example is also historically very important because it set the stage to the classification of topological phases, the classifications of anomalies, discrete anomalies, and many related things. So it's a extremely educational example that I want to explain now. So this is beyond Landau-Ginzburg. So let's discuss this model. It's a tiny, tiny tweak of this model. So by just doing a tiny tweak of this model, you suddenly get to a completely new territory, an unfamiliar territory. The tweak is that instead of having one complex scalar field of charge 1, we'll have two of them, and that's it. So this is the whole tweak. So the Lagrangian is essentially the same. But do not let this little difference fool you. It's conceptually extremely different. So let's say I goes from 1 to 2. We have two charge 1 scalar fields now, which I keep calling phi twiddle I, though it's not convenient anymore. I should probably remove the twiddle. I'll just remove the twiddle. Hopefully that will not cause a confusion. And then we have masses. And I will assume that both scalar fields have the same mass. That's very important for some things, as you'll soon see. And there will be some quartic coupling, which looks like this. So you sum over I first, you sum over the squares first, and then you take the square. That's a particular combination that will be important. There are other quartics you could write, but this is the quartic that we're going to use. And I goes from 1 to 2 everywhere. So I goes from 1 to 2. So this, in words, we can just say this is U1 plus 2 phis. Okay, that's it. So why did I choose the mass and lambda to be of this particular form? I want to preserve some symmetry. Which symmetry does anybody see? This mass, this choice of the mass and the quartic coupling are such that some symmetry is preserved. Does anybody see which symmetry I might be talking about? No. No. What is special about this combination of the sum over the squares? What does it preserve? U2. Very good. We have two complex scalars. So we preserve U2. But that's not quite right yet because, we have two complex scalars. The way they transform under the gauge symmetry, this is the gauge symmetry. Under the gauge symmetry, both scalars transform by a phase, right? So U2 contains something redundant, right? U2 cannot be the right global symmetry because this is already a gauge symmetry. So what's the symmetry that this preserves? SU2, right? So SU2 is the right answer. So the claim is simply that this choice of the mass chord and this choice of the quartic coupling are the unique ones that preserve SU2. Now, if you want to be super precise, SU2 is not the right answer either, because an element of the SU2 matrix, this is an SU2 matrix, right? But this is already gauged. So actually the right answer is not SU2, it's SU2 mod Z2, it's SO3. So the symmetry that actually acts faithfully on gauge invariant local operators is SO3, not SU2, because the center of SU2 is already a gauge symmetry that's embedded here. Okay, so we've chosen M squared and lambda to be the unique SO3 preserving masses and couplings.
Isn't SO4 the largest one?
SO4? Yeah, so if these scalars, if you thought about, we have two complex scalars, so these are like 4 real scalar fields. So there is an SO4 symmetry that acts on them. However, there is a U1 that's gauged. And we do not, and the gauge symmetries break the SO4 to SO3. The gauge interactions do not preserve SO4. The gauge interactions are only consistent with SO3, which is embedded inside SO4. Okay? There is another symmetry in this model, so we have to keep track carefully of the symmetries. So we already identified an SO. I'll be careless about distinguishing SU2 from SO3. It will not be important for this lecture. So we already identified an SU2 symmetry that acts on these two scalar fields, phi1 and phi2, by an SU2 matrix like that, right? Where U is an SU2 matrix. But there is another symmetry in this model, another continuous symmetry. I'm not going to care about charge conjugation or parity or time reversal, just continuous symmetries. So which other continuous symmetry there is in the model? One more. Hint, it appeared already before. Yes? Which one? U1 topological, very good. So another symmetry is U1 magnetic symmetry, whose current is epsilon mu nu rho F nu rho. That's the topological symmetry under which the operators that are charged are not made out of phi or F mu. The charged operators are monopole operators. They're monopole operators.
Sorry, but can you remind us how does the U1 magnetic act on the...
What I just said is that it does not act on any gauge invariant local fields. It acts on monopole operators. It's exactly the same as in this discussion. Is that okay, or should I explain again why? Because this current, the way to see it without doing any computation is that this current is not conserved due to the equations of motion. Ordinary currents in QFT, like the ones that you encounter in courses, if you have a complex field, the one current that you would see in Peskin and Schroeder is this, right? To see that this current is conserved, you have to use the equations of motion. And when you have to use the equations of motion, that typically means that there are local operators that would carry this charge. And in this case, the local operator that would carry charge is phi. I would be charged under this U1. Okay? But to see that this current is conserved, you do not have to use the equations of motion. It's conserved by virtue of the Bianchi identity. So it's independent of the Lagrangian. And that typically means that there cannot be local operators that are made out of the fundamental fields that would carry this charge. The operators that would carry this charge have to be defect operators or disorder operators, like monopole operators and twist operators and stuff like that. So the simplest operators that carry this charge are monopole operators. Okay? And they cannot be constructed using the fundamental fields. They're abstract local operators. And we had a long discussion yesterday about them. So the full symmetry of the system is SU2 times U1, which is like SO3 times SO2. It's not a big deal, right? But it's not impossible to imagine. Okay, so now let's draw the phases of this model. Oh, let's say that now you're a Landau-Ginzburg person, just for the sake of it. Somebody tells you that he found a system in the lab with the SO3 times SO2 symmetry. Let's do this kind of mental game. So you're a Landau-Ginzburg person. Somebody told you that he found in the lab a system with SO3 times SO2 global symmetry. And you have to try to predict the phases. What would you do? You would say, I have two order parameters. One for SO3, that's a vector of SO3. Another is a vector of SO2. And I write all the possible couplings. So you would write phi squared with some mass. This, right? You would just write all the possible things you can imagine, and so on. You just write some kind of Lagrangian like this, the most general possible Lagrangian, for order parameters that preserve SO3 and SO2. You could even, And then you would say, okay, so there will be some phase diagram. But at large, positive M1 squared and M2 squared, there will always be a phase, no matter what, which has how many vacua? 1. It's impossible to prevent in a Landau-Ginzburg. Any Landau-Ginzburg model that you could come up with this symmetry, I claim, it would be impossible to prevent a phase with 1 vacuum. Is that intuitively plausible to you? Because in models with scalar fields, whatever symmetries they carry, you can always add a huge positive mass to everything, and there will be one vacuum. Does that sound plausible? Surprisingly, however, in this model, there is no way to do that. In this model, there is no way to do that. So there is no way to have one vacuum. Let's see how that goes. So let's draw the phase diagram as a function of m squared, where m squared is the only relevant parameter which preserves SO3 times SO2. You could say that maybe we can add monopole operators, but monopole operators would break the SO2. So the rule of the game is that we preserve SO3 times SO2. That's the Landau-Ginzburg rule of the game, right? We only study symmetric perturbations. So we study, the only symmetric perturbation is the mass. You cannot add monopole operators, they would break SO2. And there is no other operator that preserves SO3 times SO2 other than the mass. So we study the phase diagram of this model as a function of the mass. The simplest limit is huge positive mass. But huge positive mass, it's very similar to what we did before. You just integrate out the scalars, and what do you find? You find the free gauge field. And the free gauge field has condensation of monopoles. So there is so SO3 times SO2 is broken to what? SO3, because the monopoles have condensed. So SO2 is spontaneously broken. There is a circle of vacua. And there is an S1 Nambu-Goldstone boson from the condensation of the monopole. That's just the physics of the gauge field at long distances, free gauge field. Is that correct? At huge negative m squared, the story is now more interesting than before. Before, at huge negative m squared, there was one vacuum due to the Higgs mechanism. Here, the story at huge negative m squared is more interesting. Let's try to analyze it. So what happens at huge negative m squared? Does anybody have a guess? So, yes, there is a web of defies, and how many vacua are there going to be? Yeah, so let's do just very good. Let's just do it a tiny bit more precisely. So we have two complex fields. And when we put huge negative mass squared, they're going to condense. So we have to understand how the condensate looks like. First of all, without loss of generality, we can remove one overall phase. Second of all, we can use the SO3 or SU2 symmetry to put the web in one of them. So first we use SU2 to put the web in one of them. We can always do that. So one representative of the possible, so I'm saying the web is not unique, but using the global symmetries, we can just find one representative and then understand the centralizer. Do you understand what I'm doing? I'm trying to find the most general possible web, find the subgroup that preserves this web, and then the set of massless fields will be the quotient of the symmetry by the centralizer. Sorry, by the stabilizer of the web. So we can always put the web in one place. Now, using the gauge symmetry is not a symmetry, so I'm not going to count it in the end. But using the gauge symmetry, we can take it to be real. So there is some real number, and then 0. Now we have to find the stabilizer. What is the by the way, this is the same thing that happens in the standard model, if you did not notice. Is SU2 times U1 in the standard model is the same as SO3 times SO2. So this is like reviewing some stuff that you must have seen in courses. So anyway, the stabilizer of this web is, let's see, what does SU2 do? Well, there is a difference from the standard model in here that the U1 is gauged, but the SU2 is not gauged, so one has to be really careful. So when we ask what is the stabilizer, we ask what is the global symmetry that preserves this wave. Now, for this question, we cannot use the SO2 global symmetry. That's the magnetic symmetry. The magnetic symmetry doesn't even act on phi. So we're asking what subgroup of the SU2 or SO3 global symmetry preserve this wave. Clearly, SU2 does not preserve this wave. SU2 would always multiply it by a phase, or maybe even put it in the other component. But you have to be careful, because there is a U1 gauge symmetry. So if you act with SU2 global cartan, the cartan of SU2 on this, then you would multiply it by a phase. But this phase can be removed with a gauge transformation. So what I'm saying is that the global symmetry that preserves this wave is given by the cartan of SU2, that's a global symmetry, plus a gauged U1. So if you combine a global symmetry with a gauge symmetry, you can preserve this wave. In quantum field theory, the gauge symmetry doesn't count as anything. It's something that we quotient by. So this is as good as any other global symmetry. We can always combine global symmetries with gauge symmetries. We cannot do the opposite. We cannot combine gauge symmetries with global symmetries, because gauge symmetries are gauged. They are put to 0 on the Hilbert space. But we can always combine global symmetries with gauge symmetries, because gauge symmetries are 0. So this is as good as any other global symmetry. Is that clear? Or maybe this was too fast? Yeah. Okay, so let me try to repeat it in some other way. You see, when we talk about, let's say something abstract. In quantum field theory, we have, let's say, a bunch of fields, phi I. Abstract, there is a bunch of fields. And on these bunch of fields, there could be some gauge symmetries and global symmetries. So let's say G is a bunch of global symmetries, and H is a bunch of gauge symmetries. I sometimes put gauge symmetries in brackets to distinguish them from global symmetries. You can ask first an abstract question. How does the gauge symmetry act? That's uniquely defined. How does the global symmetry act on phi? That's not uniquely defined. Why? Because we can always take combinations of G and add some components from H. This is allowed. We can always say that our action of the global symmetries can be modified by combining them with gauge symmetries. We can never do the opposite. It's like taking a quotient. We can never do the opposite. We cannot say that the gauge symmetries are modified by combining them with global symmetries. Why is there such a difference, an asymmetry? Because the gauge symmetries are put to 0 on the Hilbert space. So if you ask how the global symmetries act, then you can always add 0. But you cannot add something to 0, which would make it non-zero. So the question of how global symmetries act in quantum field theory is not well defined if you ask about how they act on local fields. It's only well defined when you ask how they act on gauge invariant operators. So one way to not have this discussion, if you don't like this discussion, and you prefer to only talk about physical questions, instead of talking about the fundamental fields, you can talk about gauge invariant local operators. On gauge invariant local operators, by definition, H vanishes. And therefore, the action of G on O is uniquely defined. Is that clear? So if you don't like this discussion of the stabilizer, you should not like it because I'm discussing questions on gauge non-invariant operators. If I discussed how G acts on gauge invariant operators, then this issue would not have come up. And I'll do it in a second. So we have these 2 points of view. They're equivalent. We can ask what's the stabilizer on gauge invariant operators, or we can ask about combining gauge symmetries with global symmetries. Sorry, global symmetries with gauge symmetries. So let's do both and see that we get the right answer. So when we ask how is that clear, by the way? When we ask how SU2 acts on phi 1 and phi 2, this is not well defined, because we can always combine it with gauge symmetries. So when we ask for the stabilizer, we're allowed to combine with gauge symmetries. And so I said here is that the cartan of SU2 global, when combined with the gauge U1, does stabilize this wave. So therefore, the stabilizer is isomorphic to SO2, because it's the cartan of SU2. So therefore, the original symmetry SO3 times SO3 is broken to SO2. So we see that the Nambu-Goldstone bosons live on the quotient SO3 mod SO2, which is the same as the two-sphere. And the magnetic symmetry is unbroken in this phase. The magnetic symmetry doesn't even act on anything here. So we see that in this phase, SO3 times SO2 is broken to SO2 times SO2. So there is symmetry breaking on both sides of the diagram. Let me now rederive it, as I promised, from the gauge invariant operators instead of talking about the gauge non-invariant ones. So we agreed, so what are the gauge invariant operators? Gauge invariant operators are, for instance, phi I, phi j star. Right? Phi j bar, maybe. I should put bar. So this is a nice set of gauge invariant operators. On them, U1 gauge doesn't act, so I don't care. Now, what do I do with the indices I and j? I can consider the combination phi 1 bar plus phi 2 bar. That's one combination. Or I consider the triplet phi 1 bar minus phi 2 bar, phi 1 phi 2 bar, and phi 2 phi 1 bar. So I can consider either this singlet. This is a singlet of SO3. It's a singlet of the magnetic symmetry, and it's a singlet of the gauge symmetry. That's the mass operator. Yeah, that's the singlet. This is a singlet under everything. So whether or not this gets Vev, we don't care. This is not an order parameter of anything. However, this is a triplet of SO3. It's a singlet of the magnetic symmetry. So it's U1 magnetic singlet because the magnetic symmetry doesn't act on any local operators made out of phi or f mu. It's an SO3 triplet, and it's, of course, gauge invariant. So now we go to this Vev that we decided we can choose without loss of generality, where phi 1 is non-zero and the rest is 0. So I should put plus complex conjugate minus complex conjugate. Phi 1, phi 2 bar minus complex conjugate. So I take that Vev, I plug it here. What would I get? I would get the vector 1, right, from this. This vanishes. 1, 1, 0. No, what am I saying? Oh, 1, 0, 0, yes. Okay, now it's a triplet of SO3. And now the stabilizer can be computed easily. The stabilizer is SO2. It's just a vector. So we get the same answer. We get S2 words of vacua. Words of vacua. Okay, so here you don't have to discuss this mixing with the gauge symmetry if you don't like it. Okay, so we see that there are two phases. On one, the Nambu-Goldstones live on a circle, and on the other, the Nambu-Goldstones live on a sphere. So we have a nonlinear signal model on the sphere on one side, and a linear signal model on S1 for Goldstone bosons on the other side. In condensed matter, this is called the VBS phase, and this is called the nail phase. That's why this thing is called the nail VBS transition. It's a transition between two phases that have these historical names, VBS and nail. And many people believe that there is a single transition, which is actually, well, we don't know if there is a conformal filter here or if it's first order. This is a subject that's under current investigation. Let me just tell you a few words about it. People don't know if there is a conformal filter that separates these two phases. It might be a first order transition. The bootstrap community has claimed convincingly that there is no conformal filter like that it must be first order. Many lattice simulations still see some sort of scaling, so we don't know. This is an open problem of whether this is first order or second order. But regardless of this question, it's easy to see that this transition cannot be in the Landau-Ginzburg family. There can be no way of rewriting this using scalar fields. So the particle vortex duality cannot apply. Something like that cannot apply here. There cannot be a dual description with just scalar fields, because any such dual description will always have a trivial phase. And here there is no way to trivialize the system. There is always either S2 or S1. You cannot have a trivial phase anywhere. So let me just mention why, for those of you who want to learn a little bit more about it. So this is a really striking example which shows that some phase transitions cannot be described with Landau-Ginzburg. That's the simplest example. So let me explain. So there is an explanation nowadays of why this model cannot be trivialized. So I'll give you a quick explanation without any details, just some, it's just buzzwords so that you know the buzzwords. So the explanation is that the symmetry of the model is SO3 times SO2, but it turns out that there is a 't Hooft anomaly. Even though this model is bosonic, you might have learned about anomalies of fermions, right? About this. You learned about this, right? The fermion anomaly. And what you might have learned in school is that this kind of thing can appear only in 4 dimensions or 2 dimensions, and only when there are chiral fermions. Is that right? All of this is wrong. 't Hooft anomalies can appear also in odd dimensions, and you don't need fermions. This is an example. So this can appear in odd dimensions, no problem. And you don't need fermions. It can appear in completely bosonic models. And the simplest example is this model. This is the simplest example of a model without fermions in odd dimensions that has a 't Hooft anomaly. And the 't Hooft anomaly involves SO3 and SO2. We sometimes denote it like this, that the anomaly involves both. Because there is a 't Hooft anomaly, so when there is a 't Hooft anomaly, you might have learned that you have to match the anomaly. Does that word sound familiar? Matching the anomaly means that there cannot be a trivial phase. When there is a 't Hooft anomaly, we say that there is no trivial phase. There must be massless fermions, or maybe some Nambu-Goldstone bosons, right? Like in QCD, there is a chiral anomaly, so we have Nambu-Goldstone bosons. So there cannot be a trivial phase. You must have either Nambu-Goldstones or some symmetry breaking, or maybe massless fermions or something else, or gapless stuff. So this is the same here. There is a 't Hooft anomaly. It's in odd dimensions. There are no fermions, but the implications are the same. You must have either Nambu-Goldstones or maybe or some other gapless stuff. Or some other options also exist that I'm not going to explain. So there is a proof that this model cannot be trivialized. And this also actually proves that it's beyond Landau-Ginzburg. Because any Landau-Ginzburg model cannot have an anomaly, by definition. So Landau-Ginzburg models can always be trivialized, and so they cannot have anomalies. Cannot have anomalies. So you see that basically the way to go beyond Landau-Ginzburg is to cook up models with anomalies. Landau-Ginzburg model cannot have anomalies. Okay, so I'm not going to prove that there is such an anomaly. This is quite tough, but I can give references for those interested. I just gave you like the gist of the story. Are there any questions about it? Yes.
Does this model describe some kind of material?
Yes.
What kind?
So that's a part that I did not want to go into too much, but I can tell you a little bit. Before I go to that, are there any questions about the formal statements? That what you learned about anomalies is not true? You don't need fermions, you don't need even non-dimensions, and this is how we see that this model cannot be Landau-Ginzburg. Are there any questions about the formal statements? Okay, so regarding the question of which materials he describes, well, if you really want to learn about it, you just put in Google Nail VBS transition and you'll see thousands of papers. But roughly speaking, these models are quantum antiferromagnets. That's the. So let me just say a few words about it. I introduced a few quantum phase transitions in the first lecture and the second lecture. They involved typically ferromagnets, like this transverse field, the Ising model, or the original Ising model. But actually, it turns out, this was understood in the 90s and 2000s, that antiferromagnets, where there is a repulsion between the spins, lead to these highly non-trivial phases of matter that cannot be perturbed to trivial phases. And so antiferromagnets are generally more rich. And there is a theorem. So I proved. So the way to prove, as a quantum field theorist, the way you prove that this model cannot be trivialized to a trivial phase, I mean, and cannot be described with Landau-Ginzburg, is that you prove that there is some 't Hooft anomaly. That's how you do it as a quantum field theorist. In condensed matter theory, there is a different technique, which is called Lieb-Schultz-Matisse. So Lieb-Schultz-Matisse. This is a different technique that condensed matter people developed more or less independently, but it's basically the same. So Lieb-Schultz-Matisse theorems apply to lattice systems of antiferromagnets. And what these theorems prove is that these antiferromagnets cannot be in a trivial phase. So they prove that either it's gapless or there is symmetry breaking. That's what these theorems typically prove. So you can learn about it there is lots of papers about it. Either gapless or symmetry breaking. And it's kind of the same as 't Hooft anomaly in quantum field theory. There is lots of recent work on people trying to show that it's actually the same. That Lieb-Schultz-Matisse and 't Hooft anomalies is the same thing. These are still some things in development, but basically that's the message. Any other questions? Yes?
How do you trivialize the Landau-Ginzburg model if you're given one? Is it obvious that the statement is true?
Well, Landau-Ginzburg models are just models of some fields with some quantum numbers under the global symmetries. So if you put a huge positive mass squared to everything, you can always trivialize it. There cannot be no obstruction. There can be no obstruction to that. But in this model, you see that no matter what you do, as long as you preserve all the symmetries, you cannot trivialize it.
And in this code above, how to see the number of phase transitions?
Nobody knows the answer. The question of what is the nature of the phase transition is an open question.
I was asking about the number of.
Even that is not known with certainty. People believe it's one, but it's not known with certainty. All we can prove without doing, hardcore analysis is that there cannot be a trivial phase, and there has to be at least one phase transition. And so, therefore, it's not Landau-Ginzburg, but what exactly it is, we cannot analytically answer this question at the moment. Yes?
So why are we not told that that's not true?
It's because most people don't know that this is not true. When the books, like when Peskin and Schroeder was written, they didn't know that this is possible. Huh?
They still,
Yeah.
they still say it.
Yeah. Yeah.
In the literature, I've read a lot of different statements about how one can classify these anomalies.
There is a lot of work on that nowadays, on classification.
What is the best one or yes?
No, the answer is already known.
Because somewhere that is cohomology stuff is most general, somewhere else cohomology is most general, with most general.
I believe that this question is settled.
Okay. And with the answer?
Hmm?
And with the answer?
I don't think it's useful to discuss the answer now. We can discuss it because it's extremely technical. But the classification of which dimensions and which anomalies can appear is, in my opinion, a settled question.
Okay.
Any other questions?
What are they?
You want the answer?
No, but what is soft anomaly?
You're asking what?
Something that you didn't explain.
I'm not going to explain that. I'm just giving you the buzzwords, so those interested, that there are some phase transitions beyond Landau-Ginzburg. They have to do with anomalies. Maybe some people here saw anomalies in courses. I'm not going to teach anomalies. that would be like 10 hours course. I prefer to move on to some new stuff. So I just gave you the buzzwords if you want to learn about it. Any other questions? I'm now going to switch to go to a new subject. So let me explain the conceptual. We're going to some new conceptual territory, and I want to explain what is this conceptual territory. So if you think about what we've done so far very abstractly, like zooming out, we have seen some examples of systems where there are some order parameters. These order parameters could be magnetic monopole operators. They could be some triplet, like the triplet we just saw of this 5 bar. We basically saw some order parameters of some symmetry G. Very abstractly, right? We discussed many examples of symmetries G, like SO3 times SO2, SO2. And we discussed several types of order parameters, like monopoles, scalar bilinears. And then we saw phases. The phases sometimes had non-zero expectation values, sometimes 0. And we saw various phase transitions. We even saw one phase transition where at every phase some order parameter condensed. So you couldn't trivialize the model. You couldn't trivialize the vacuum. But basically the phases that we saw so far had some order parameter condensation taking place. This already leads sometimes to models that are beyond Landau-Ginzburg. Now I want to start introducing a new subject, which is even more interesting conceptually. You could ask, do all phase transitions have something to do with the condensation of order parameters? Do all CFTs, instead of talking about phase transitions, let's say CFTs, do all CFTs have something to do with condensation of local order parameters? That's a big conceptual question in statistical physics or in quantum field theory. Like, is that everything that we're going to ever talk about? Some formal field various orders. And the answer to that is more generally, the answer to that is no. And of course, that's also way beyond Landau-Ginzburg. In Landau-Ginzburg, the answer is yes. Let me just say that. In Landau-Ginzburg, the answer is yes. So the answer is yes, also sometimes beyond Landau-Ginzburg, as we saw in this recent NeL-VBS example. So in Landau-Ginzburg, the answer is yes. And also in the NeL-VBS model, the answer is yes. But there are more sophisticated, more interesting questions in quantum field theory that lead to the answer no. And so we will now start learning about topological order. What is topological order? Let me explain the word topological and the word order. Order is like in a magnet where all the spins point up. There is some symmetry breaking and it seems ordered because all the spins are pointed in the same. There is a lot of order in the system. But when you have a magnet and all the spins are pointing up, right? You can see this order. You don't have to look at the whole magnet to see this order. You can just zoom in and you see, oh, in a small region, everything is pointing up. So there is some order. You can see it locally, right? So this is you can locally observe that there is some order. But sometimes the order cannot be seen by any local experiment. So to see that there is some order, you have to look at the whole material at the same time. And that's when the word topological comes in. Okay, so sometimes the materials are ordered, but in a way that cannot be observed by any local measurement. No local operator can detect this order. So no local operator can detect. So to see that there is some order, you have to look at the whole system in one swipe. And topological order is not a unique thing. Like ordinary order can come in many different guises. There could be order for O3 symmetry, O2 symmetry, that breaking, this breaking. Topological order could come in different guises. So you could have some topological order here and a different topological order here. If two phases of matter have different topological orders on two sides of the phase diagram, there must be some phase transition. You must close the gap or have a first order transition. You cannot go from one topological order to another topological order without ever lowering the gap to 0 or having a first order transition. So the idea of topological order is that this is some kind of more abstract concept that cannot be detected by any local measurement. This is very interesting for quantum computing and quantum theory for the following reason. So imagine, for instance, the cockpit of an airplane, and you want to protect it from kids, right? The kids would run and start clicking buttons, and the airplane would fall. But imagine that you protected it in such a way that no random clicking on the buttons would do anything. You have to correlate the clicking in different places in the cockpit in some very convoluted way so that the airplane would react. So topological order is very interesting to quantum computing because no local interaction can kill it. It's something that takes place everywhere in the universe at the same time. So you need some coherent disturbance to kill it. And it's so much more resilient. Topological order is resilient to decoherence or to environment perturbations. So you can maintain coherence more easily. And that's, of course, one of the challenges in quantum computing. So that's the reason that condensed matter theorists are interested in topological order. From the particle physics point of view, or quantum field theory point of view, this is a conceptually new class of phase transitions with various interesting questions in QFT. And they appear in many applications in QFT. So one can study them for their own sake. So this is the general. Are there any questions about? This is the direction that I'm going to go into now. I'll teach you a little bit of topological order, and then we'll discuss maybe one or two examples where this happens. Any questions about the introduction? Yeah.
What can we say about the transition between two topological?
So oftentimes you cannot say much, but sometimes we'll have a duality. We'll be able to guess what it is. But in many cases, you don't know. You just have to measure it.
Say it's a first order or second order, just
These things are typically beyond our analytical abilities. But you can try to guess it. If you have a good dual description that you found by guessing, then you might have a guess for what it is. But generally, the interesting concept is that sometimes some phase transitions do not take place between orders that are locally observable. And of course, it goes without saying that this is beyond Landau-Ginzburg, because there is no topology in models of scalar fields. In models of scalar fields, like Landau-Ginzburg models, there cannot be any topology. Any other questions about the introduction? Okay, so now we go to the example, the abelian ChernSimons theory. That's the first example of topological order. So I'll start with some kind of a gentle introduction to ChernSimons theory, connecting it to what we discussed so far. And I won't discuss the topological order immediately. I'll first discuss some more basic properties of ChernSimons theory. And then we'll get to the topological order So we start again from our favorite model, which is free Maxwell in 2+1 dimensions. And we discussed that this model has one massless degree of freedom. And we also said that you can think about it as a single scalar field, but that would not be useful for now. We also described yesterday a way to give it a mass. So there is a canonical way to give this photon a mass without having a Higgs field, which is what? How can we give it a mass? Yeah, we can add monopoles. By adding monopoles, proliferating monopoles, I should say, we saw that we could give this photon a mass, and then we get a degree of freedom which is massive and spin 0. So we get a massive degree, spin 0, massive degree of freedom. And parity odd. Spin 0, parity odd, massive degree of freedom. So we know already of one mechanism to give the photon a mass. But in 2 + 1 dimensions, there is another mechanism to give the photon a mass with a completely different outcome. Instead of a massive spin 0 parity odd particle, you get a spin 1 massive particle. And this is the Chern-Simons interaction. This is something that's peculiar to 2 + 1. It's a peculiar interaction in 2 + 1 dimensions, which we'll now discuss. So what you'll see soon is that with this interaction, the photon will become massive, but it's not the same as this. It will have spin 1 or -1, depending on some conventions. So let's start discussing that. Now, this Lagrangian famously, despite appearances, is gauge invariant. So let's do the gauge transformation of this Lagrangian. So by appearance, this Lagrangian looks weird because it's not made out of the field strands, but famously it is gauge invariant. Because if you do the gauge transformation, you don't have to vary this guy because this is the field strands. So you just have to vary this guy. So you have epsilon mu nu rho, d mu omega, d mu a rho. And this is formally a total derivative of epsilon mu nu rho omega d nu a rho. So since this is a total derivative, the gauge variation is a total derivative, you could say that if you were to integrate, the gauge variation would be a total derivative, and it would vanish. This is what you would see in the books. This is, however, incorrect. It's not completely correct. Why does anybody have a guess why this is not? We discussed actually why this is not correct yesterday. Why is this argument not completely correct? There is some issue with the integration by parts. But more importantly, we use the Stokes theorem here. And what did we say yesterday? Are we allowed to use the Stokes theorem? When are we allowed to use it? When the thing inside the parenthesis is a good form. But here, the thing inside the parenthesis is omega, epsilon mu nu rho, d nu a rho. So let's discuss this object. Is this a good differential form? Is this a good differential 2 form? Is this a good 2 form? Can we really use the Stokes theorem? Well, f nu rho is a good 2 form. But omega is not a good 0 form. Because you remember that omega is the gauge parameter. And in what condensed matter, in condensed matter is called non-compact U1, omega is actually a good function. It's a good 0 form. It's a function from space to R. And that's, by definition, that would be a good 2 form. Because omega is just a function. So if you are discussing non-compact gauge theory, you don't have to worry. This is a correct argument. And K can be anything. It doesn't have to be quantized. So if you're discussing in U1, if you're discussing the non-compact gauge theory, K can be anything. It doesn't have to be quantized. Because this is a good 2 form, so the Stokes theorem is valid. But if you're discussing what I'm interested in, which is U1 gauge theory, in U1 gauge theory, omega is a function from space to S1. It's not a good form. It's not a good, so when you compare two different patches, so suppose you have two different patches, you have to compare this and this guy here and this guy here, they might differ by 2 pi, because omega is not a function, it's a circle valued function. And this is not how two forms are supposed to transform when you go from patch to patch. Okay, so this object is not a two-form because it doesn't transform like a two-form. It can pick up an inhomogeneous piece. So therefore, this argument is not correct. But as we saw yesterday, it's not like this argument is completely flawed. When this is not a good two-form, it means that this argument might not be correct, but the mistake that you would make is an integer. You remember that from yesterday? And for that reason, when you're doing compact U1, which is again grammatically silly to say, but where you're doing compact U1, k must be an integer. That's what you find in this convention. And for this, the 4 pi is crucial, because in this quantization, some integer pops out with some 2 pi, and it's crucial to get the 4 pi straight. So k has to be an integer. So the model is only well defined when k is an integer. So from now on, k will be an integer. And I arranged for the 4 pi's to be such that this works out. Okay, so what is the physics of this model? Let's do classical physics first, or let's say just the equations of motion. So the equations of motion for this model are I'm being careless about coefficients. You can stick the coefficients back at home. So the equation of motion is d mu f mu plus epsilon mu alpha beta f alpha beta equals 0. That's the equation. Oh, and k. I'm going to put a k symbolically. So this is the equation of motion, right? Does everybody agree? So to analyze the solutions to this equation, so this is actually an interesting equation. As you remember, without this term, there are waves. There are massless waves, Maxwell's waves, the electromagnetic waves. But with this term, these waves don't exist as you know them. There is a modification. So there is a quick way to see what happens in the presence of this term, is to slightly change variables. So it's somewhat useful to introduce f twiddle mu, which is epsilon mu nu rho f nu rho. That object we already encountered in the duality with the scalar, if you remember. So let's just rewrite this equation for f twiddle mu. So we get d mu epsilon mu alpha beta plus k delta alpha beta. This differential operator, when it acts on f twiddle beta, gives 0. Okay. That's just a silly way to rewrite this equation, but it's not useful yet. So to make it useful, I should have emphasized that k is dimensionless. It's an integer. And E squared has dimensions of mass. That will be useful soon. So E squared has dimensions of mass and k is dimensionless. Okay, so let's consider this equation. And let's multiply this equation by another. So I'm just going to add something. Alpha. So let's say gamma delta alpha gamma delta alpha minus k delta alpha mu plus k delta alpha beta f twiddle beta. So I didn't do anything. I just took this differential operator that annihilates f twiddle and I multiplied it by something that contracts with the index alpha. So this is allowed. And the mixed term here cancels out. When you open the differential operators, the mixed term cancels out. If I did not make a sign mistake here. And what you find after you open the parentheses, oh, and you have to use one more fact, which is trivial, that d mu f twiddle mu vanishes. That's the Bianchi identity. So opening the parentheses and using this fact, you find d squared minus k squared on f twiddle mu vanishes. So this f twiddle mu obeys a Klein-Gordon equation, but not a massless one, a massive one. So you can read out the spectrum quickly in this way. So we see that now there is a mass. It's called the ChernSimons mass, MCSM. And it's given by k, and I have to put back the units, so I have to use E squared. That's the deep formula. So there's yet another mechanism to give the photon a mass. There are no massless degrees of freedom in the system. You see that this equation implies that all the solutions will be solutions of the massive Klein-Gordon equation, not the massless one. So there are no waves anymore. There are no waves that move at the speed of light. The waves obey now a dispersion relation, which is the standard omega equals square root of the momentum squared plus k squared. So there are no more, what did they do? Yeah, so there are no more massless waves. Also, another thing you see from this equation is that the waves now have spin 1. But you have to be a little bit careful about it. You can ask, what is the spin? In 2 + 1 dimensions, the little group is so in 2 + 1 dimensions, when you have a massive particle, you can just put it at rest. And then the spin is the eigenvalue of the rotations. So it's a U1. But as you know, the spin doesn't have to be an eigenvalue of the actual rotation symmetry. It can be an eigenvalue of the cover of the rotation symmetry. That's why we have spin half in 3 + 1 dimensions. So, well, in principle, the spin of this particle can be either 1 or -1. Unlike in 3 + 1 dimensions, this is not the same thing. You can have that their eigenvalue is 1 or -1. These are different things. So you have to do some careful analysis to understand if the spin of this excitation is 1 or -1. That does not yet follow from this equation. You have to do a slightly more careful analysis. I'll show you how to do it in a second. What you find after the analysis is that the spin is k over absolute value of k. So if k is positive, the spin is 1. If k is negative, the spin is -1. So what this system describes is a massive spin 1 particle, a single degree of freedom, not 2, 1. So it's not like the Higgs mechanism. In the Higgs mechanism, we would have 2 degrees of freedom. Here there is 1 degree of freedom of spin 1, either 1 or -1. So we have 1 massive degree of freedom with a spin being 1 or -1. The reason that the spin flips from 1 to -1 is intuitively clear, because this term has an epsilon tensor, so it's parity odd. Parity flips the spin. So when k goes to -k under parity, the spin flips from 1 to -1. So you can explain this pattern by thinking about parity, which flips the spin. If something is spinning like that, when you apply parity, the spin reverses. So basically now we have, instead of a massless photon, we have a single particle with spin like that or spin like that, with some mass which is given by this formula. Okay, so that's what the Chern-Simons interaction does. It seems very interesting, but has nothing to do with topology, right? It just makes the photon massive and that's it. Who cares? So after the break, we will analyze Oh, before the break, one last thing before the break. I promised you that there is another way to extract the spin. So let me just do that quickly. So if you don't like this sort of thinking, you can just compute the propagator, like old-fashioned QFT. You can compute the propagator, which is A mu, A nu. You do that by standard Peskin-Schroeder techniques. You diagonalize the propagator, you pick a gauge, and you find the following propagator. What you would find is that the propagator is p squared g mu nu minus p nu plus I. This is again without coefficient, without various coefficients. I only kept some coefficients. Mu nu rho, p rho. This is divided by p squared minus k squared e squared e to the 4. And then there is this Xi term. This is in Xi gauge. Okay, that's the propagator that you would find. Yeah. So you can reproduce it at home. That's the propagator. And there is something very interesting about it that you may not have seen in your courses. So this propagator, so first of all, we see a pole at k squared e to the 4. That's great. That's exactly where the ChernSimons term is supposed to put the massive photon at. That's exactly the physical mass. But there is something really disturbing about this propagator, which is that there is another pole. Here, you see? There is another pole at p squared equals 0. This is unexpected. In fact, we proved using this classical analysis that there is no degree of freedom in the system that can move at the speed of light. The degrees of freedom inside F mu, the electric fields, the magnetic fields, they satisfy the Klein-Gordon equation, so they cannot move at the speed of light. They satisfy the massive Klein-Gordon equation, so nothing here can move at the speed of light. So how is it possible that there is a pole at p squared? This is a puzzle for you to think tonight. Let's see, will somebody figure out the answer? And finally, once you figure out this answer and you understand why there is a pole at p squared equals 0, you can go on the actual physical pole and do the analysis of the spin by asking whether the numerator rotates like z or z bar. So you just this is the standard LSZ. So by using standard LSZ, you can then extract the spin from looking at the properties of the numerator when you expand around the pole. And then you will see that the spin is either 1 or -1, which is kind of almost clear, because when k flips the sign, it's like z bar, and when k is positive, it's like z. So it's almost obvious. That's it. So let's take a break now. Are there any questions? I got many good questions over the break. Unfortunately, I cannot. You should have asked them during the talk, but so that no. Are there any more questions? Yeah. Okay. So now, well, when you see such a thing, I mean, we just described the system, which has a massive spin 1 particle, and it's totally boring. It's a free system. It satisfies the Klein-Gordon equation. The massive Klein-Gordon equation, it's a free massive particle. When in quantum field theory you learn about systems whose, there is a particle at mass m, what would you expect the theory to do at very low momentum, at 0 momentum? What would there be at the very, very low energies? What's your expectation when you see a theory like with a massive particle? What happens at very low energies? Is it trivial or is it not usually? Yeah, usually there is nothing, right? So usually when there is a massive gapped quantum field theory, there is just nothing below this mass. But that's not the case here. And that's the main topic. So the main topic is to tell you that even though you might think that there is nothing below the mass m, which is given by k e squared, there is actually extremely rich physics below that mass. So there is topological order So the vacuum is unique, but it's topologically ordered. And I want to show you what does that mean. So one way you could try to convince somebody that the vacuum is topologically, you have to decipher what this means. When I say that the vacuum is topologically ordered, it doesn't mean anything. So you could think about it in several different ways. What does it mean for the vacuum to be topologically ordered? One way you could think about it is that suppose you are a very powerful experimentalist with access to the system, you could try to measure, for instance, the wave function, something like the wave function of the vacuum in some variables. And for completely trivial systems, like massive particles, bosonic, like for completely trivial systems like massive bosons, Landau-Ginzburg type systems, to a very good approximation, the ground state wave function is just a product over all space of some kind of harmonic oscillators. You might remember that. So there is a harmonic oscillator in momentum space, and you just take a product over everything. So it's approximately a direct product. So a direct product over all of space in some formal sense. So one way in which we mean that the wave function is not, that there's topological order, is that there's something intrinsic about the wave function which is not like that. So there is some kind of entanglement. That's the key word. So there is entanglement in the vacuum. So there is entanglement in the vacuum wave function. Okay, that's one way you can think about. So the vacuum wave function being non-trivial is that there is some sort of entanglement inside. Another way in which you could say, in which you could sort of experimentally decipher the words topological order is that suppose you don't have access to the full wave function, but what you can do is that you could, instead of studying the system in flat space, which is flat space times time, right, which is what we're doing, you could say, put the system on a torus times time, or a sphere times time, or some other compact manifolds times time. And for topologically ordered vacua, like in this system, they would exhibit a different number of ground states on different topologies. So the number of ground state wave functions would be a function of the topology. For ordinary Landau-Ginzburg models like massive bosons, the number of ground states on any topology is 1. For systems like this one, the number of ground states depends on the topology of the manifold. So that's another way in which you can experimentally see that the vacuum has some topology in it. I'm going to try to compute the entanglement entropy here, and I'm not going to try to explain to you how to quantize the systems in compact space and show that there is a ground state degeneracy that depends on the topology. What I'm going to do is I'm going to show you that the vacuum responds non-trivially to probe particles. You could do some Gedanken experiments in R2 with some probe particles and see non-trivial long-range forces or long-range effects. So what we're going to do is a third approach. We're going to follow a third approach, not one, not this one, and not that one. We're going to follow a third method in which we introduce probe particles into the vacuum, some heavy probe particles, and we will see that they exhibit weird non-local effects. So they will exhibit weird non-local interactions. So that's the third approach. That again, of course, does not happen in Landau-Ginzburg models. If you're in a massive phase, there's nothing in the vacuum. But here you'll see that probe particles exhibit weird non-local interactions. And that sort of signals that there's something going on in the vacuum beyond the usual expectations. Okay, so that's the method that I'll follow. Are there any questions about the general approach to deciphering what it means for the vacuum to be topologically ordered? Of course, now there's a lot of work on entanglement entropy. So this is an approach, this is a question that many people study. but we'll take this approach. It's much easier to compute. So what we're going to do is that we're going to take the ChernSimons action. Oh, I'm going to explain what I'm doing in a second. So I'm interested in asking what happens at extremely low energies. I want to convince you that something is going on at extremely low energies, much below the mass scale of the massive photon, the spin 1 excitation. So looking back at this Lagrangian, how do we go to very low energies? That's a general idea in this field. How do we go to very, very low energies? This has two derivatives, right? And this has only one derivative. So you might expect intuitively that this dominates at very, very long distances. So you can throw away the kinetic term. Another way to think about it is that the mass of the massive photon was k e squared, right? It was k e squared. That was the mass of the massive photon. So let's just formally take e squared to infinity. And that way we get rid of this massive spin 1 particle. And that's the same as erasing this guy. So it's like taking e squared to infinity. So taking e squared to infinity, we sort of erase this massive spin 1 excitation, and we're left with just the low energy physics below this mass. So these two things are completely equivalent. We just take so what I'm going to do is just keep this term. I'm going to throw away the kinetic term, because the kinetic term doesn't play any role at low energies, at energies below the mass of the ChernSimons photon. And we're going to couple a mu to a classical source. This is going to be completely classical. And I'm going to just, I'm not going to write the word classical, I'm just going to write C, like this. So J mu is a classical function. It's not quantized. And I'm going to discuss the response of this theory to classical sources. So let's write the equations of motion. Here the coefficients are actually somewhat important, so I'll try to get them straight. So k over 2 pi, k over 4 pi epsilon mu rho f mu rho, maybe I put a minus sign here, is equal to J mu classical. Okay, that's the equation of motion. And we can write it, we can just recall that J0 is the charge density and Ji is the current. Notice that from this equation, taking a divergence, we see that the classical source has to satisfy this equation, which is called the continuity equation, right? This is a necessary requirement from any consistent source in classical electrodynamics. It has to satisfy the conservation equation. So if charge moves, there is Ji. Okay, so J0 is rho, then Ji. So we can write this equation in the following way. Rho classical, the classical charge density is going to be the same as k over 2 pi times the magnetic field. And Ji is going to be classical, the same as k over 2 pi epsilon ij times the electric field. So these are our equations. These are our Maxwell equations, so to speak, but there is no, it's the ChernSimons. There is no Maxwell term anymore. These are very peculiar equations because they're first order equations. In Maxwell's theory, once you fix the charge density, you cannot fix the solution uniquely because there are waves. But here, once you fix the charge density, the magnetic field is fixed completely. And once you fix the current, the electric field is fixed completely. There are no waves in this system, and that's not surprising because once we've thrown away the propagating massive spin 1 particle, we've thrown away all the propagating degrees of freedom. There's only topology now. There is no more propagation of stuff. Okay, so it's a peculiar system of equations. Let's try to understand what the solutions are. So an interesting source. So I'm going to study the following source. I'm going to put the currents to 0. So I'm going to just put probe particles at designated positions, and they're not going to move. And the charge density is going to be a sum from I to n of delta functions of x minus x I. So the picture is that I put charges at rest at various points. So from these equations, we see that the electric fields vanish. There are no electric fields. That's a little weird, right? If you're used to classical electrodynamics, there are electric fields from charges. But here, there are no electric fields. These charges don't emit any electric fields. However, there are magnetic fields. But the magnetic fields are localized to the particles. The magnetic fields don't spread out in space, because in this limit, the particle is sort of infinite. So the magnetic fields don't spread out in space, and they're completely localized to the particles. So these particles started their life as electric sources. These are electric sources. But instead, what happened to them? They become little solenoids. So there is a magnetic field that goes through the particles now. I could have put Qi here. Qi is the charge. Qi some integer. Okay? This is the integer charge of that probe particle. So each particle becomes a solenoid with magnetic flux through the solenoid that is given by 2 pi Qi over k. So that's the magnetic flux through a particle of charge Qi. So each particle becomes like a little solenoid in Chern-Simons theory. And there are no electric fields. So what happens classically in this system? Classically, it's completely boring. Okay, so there are solenoids and they move around, and that's it. If you push them around, they'll move around, and that's it. But in quantum mechanics, solenoids are very interesting. Does anybody remember why? Why is this quantum mechanically very interesting? Yes, the key word is Aharonov-Bohm. So classically, that's all there is to say about Chern-Simons theory. There is no propagation, and there is just little solenoids, and they move freely in space. But quantum mechanically, something really interesting is going to happen now when they move around each other, right? Because there is an Aharonov-Bohm phase. So let's take a particle with charge Qi, and it becomes a little solenoid. And another particle of charge Qj, and that also becomes like a little solenoid. And let's imagine that this guy moves around this guy, just very, very slowly. The wave function will pick up a phase. What is the phase? Phase ij. What is the phase that it will pick up? The phase that it will pick up is given by a product of the electric charge of this guy times the magnetic charge of this guy. So it will be Qi, Qj over, so the magnetic flux was 2 pi over k. So the phase is going to be, it's going to have a k, and it's going to be 2 pi. So that's the phase. 2 pi Qi Qj over k. I just multiplied the electric charge by the magnetic charge. And this is symmetric under ij. So when this particle moves around that particle, we pick up this phase. And this has a far-reaching interpretation because this phase doesn't depend on the distance between these particles. They could be in different galaxies. That means that in the vacuum there is something is there, right? The vacuum is not completely trivial. You put probe particles in different galaxies, you move them, and then there is an observable phase. As Aharonov and Bohm argued, this phase is observable. This phase would affect interferences. This phase would even affect the energy spectrum if you do first quantization of heavy particles moving in this background. So this is an observable phase. That's what Aharonov and Bohm proved. And the fact that this phase exists, even for particles that are far apart, like one is here and the other is in another galaxy, this means that there's something in the vacuum. The vacuum is not totally trivial. So there is something in the vacuum. Let's a little bit describe in more detail what's going on here. So one way you could try to think about, are there any questions about this computation? It's a very important computation. Yes?
How do you say that the particle must be very slow? Must go very slow?
Yeah, must go very slowly.
And why?
So you remember that this setup is in some low energy approximation. So if you carried it very fast, you might excite the spin 1 particle, and then this computation breaks down. So you want to stay adiabatic. You want to do this process much, much slower than the gap. Then you really probe the vacuum and not some excited states. Yeah.
How have you computed that phase?
So in Aharonov-Bohm, what did Aharonov-Bohm find? They find that if you have a solenoid with magnetic flux B, and you carry something with electric charge E, then the phase that this will pick is E times B. So I took E, which is Qj, and multiplied it by B, which is given by this. So I just multiply these two things. Okay. There is another very useful concept in this business, which is the following. You might think about these particles as in first quantization. So this particle will be in some position xi, this particle will be in some position xj, and you have some wave function. And what we've shown is that if we carry xj around xi, the wave function picks up a phase. But there is another thing that is very familiar from quantum mechanics that might appeal to you, which is that if we interchange the two x's, we can extract the spin of the particle. So we can try to associate intrinsic spin to these things. And the spin is going to be 2 pi I times the spin. So I'm going to take two copies of the same particle, qi and qi, carry it around, and then extract the spin from this formula. So this is going to be a generalization of Fermi-Dirac statistics, because we will get fractional spins. Not a half and not one. We'll get funny spins. So let's do this computation. So we take the particle qi with this solenoid, and we take another copy of the same particle. We take identical particles, like in Fermi-Dirac statistics. We take identical particles, and now we carry this whole way around the other particle, and then the phase that we pick is from, I'm just using the formula that's on the board, is 2 pi over k times q squared. Right? But this is not the same as this phase, because here what we want to do, we want to exchange their places. And here I did not exchange their places. I took it all over around. So how do I get from this to the spin? Does anybody have an idea? How do I exchange the places rather than take the whole thing around itself? Half. Spin is just a half of the phase. So the spin is qi squared over 2k. That's the important formula. Write it down. So if you start from an electric particle in ChernSimons theory with charge k, it becomes a solenoid and it picks up fractional spin. So electric particles become So electric particles become solenoids, little solenoids, and then they pick fractional spin. How are particles with fractional spin called? They have a name, anyons. So the vacuum of ChernSimons theory, in the vacuum of ChernSimons theory, pro-particles become anyons. And anyons have funny statistics. A very interesting example that there is a very special case. Well, before I get to this special case, okay, so they pick up this fractional spin. I want to make an observation, an important observation, which is about the phases. You can ask, how many distinct anyons are there? So I can put charge 1, 2, 3, 100. Pro-particles with different charges would be like different anyons, right? But how many anyons are there really there? If you take the phase of two particles, this is invariant under taking each charge and shifting it by k. Do you see that? So the phase is invariant under shifting the charge by k, because if the phase is a multiple of 2 pi, we're in business. Similarly, if we shift the charge here by k, the spin would shift by a half or 1. So that would be like the spin of an ordinary particle. So the bottom line is that when you go to this long distance limit, you would not really be able to measure the charge of the particle. You would only be able to measure it mod k. You see why? Because if you're a long distance experimentalist, you see some anyons, you can measure their phases, you can measure their spin, but you cannot measure their charge better than modulo k, because you cannot measure the. You can measure. You could say that you can measure their spin, but of course, let's take an anyon, and we can put on top of it a little massive particle of spin 1, like the ChernSimons particle that we found. So how would you distinguish these two? You cannot distinguish them at long distances. And the phase doesn't give you information on q better than q modulo k. So to make a long story short, there are basically k anyons. So the number of anyons at long distances is finite. This is another way to understand the quantization condition on k. So previously I argued that k must be quantized, and you see that if k wasn't quantized, there would be infinitely many anyons, which is not a healthy theory. We expect topological phases to have finitely many anyons. I want to make a small footnote for the advanced students. Most of you should freely ignore what I'm saying now. There is actually a distinction between even k and odd k. For even k, what I said is true, but for odd k, there are actually 2k anyons. Okay, there is a small technical distinction that I'm not going to explain. I just note it for the more advanced students, and if you want to read about it, you have to learn the distinction between spin topological field theory and non-spin topological theory. This will not be important for this course. This is a subtle but important distinction if you want to get into the details of this subject. But basically, the number of anyons is finite, and it's k or 2k, depends how sophisticated you want to be. So the existence of the anyons in the vacuum of this theory is a telltale signature for topological order. That's the idea. Existence of anyons is a signature for topological order, and that never happens in ordinary systems with bosons, without gauge fields. Are there any questions about the probe particles in ChernSimons theory? Yes.
You said that if I attach the spin one particle to one of the anyons, right, experimentalists cannot distinguish.
Yeah, because think about an experimentalist that's doing measurements with very low energy access. So these anyons, from your point of view, what is their mass? It's just probe particles. From your point of view, these probe particles have infinite mass. So how an experimentalist is going to be able to tell one probe particle from a probe particle on which you put another little one?
Already in our approximation, wasn't also the spin one particle very massive?
Yeah, that's what I'm saying. So once you take a particle and put another spin 1 particle on top, you change the spin by how much?
Yeah.
By 1. And therefore, you cannot really measure the spin better than modulo k. Better than modulo 1, which means that q cannot be really measured better than modulo k. So I'm just giving you an intuitive explanation for why the number of anyons has to be deemed finite. Because the low energy experimentalist cannot say what is the spin. He can only say what is the spin modulo 1. That's it. And also he cannot measure the phases. He can only measure the phases mod 2 pi. So he cannot do better than just say which of the k anyons you are dealing with. But he can say that there are k anyons, and that's good. That's good enough for topological order. Yeah. Any other? There was another question. From? Okay.
A very basic question, sorry. When you study the iron moment factor, at least the one that I know is you take a very small particle, a quantum particle, and you move it around something classical like a solenoid.
Yes.
Okay. And here, from my understanding, we're not in that picture because we have two solenoids. So we have that flow only if the length scale of the solenoid, I mean the probing solenoid, this one, is very small, and I can apply the rule of quantum mechanics.
Quantum mechanics is not about small or large. The Aronoff-Bohm effect is true, always. There is no assumption in the Aronoff-Bohm effect that something is small or something is large. I can give you a mathematical explanation, or do you want exactly what?
It's easy to understand.
Not sure. I mean, you're saying that the Aronoff-Bohm effect depends on assuming that something is small. I'm not sure what you mean.
I mean, that's the intuition that I had about that.
H bar is set to 1 in this course.
So, when we spoke about the topological trivial pattern without entanglement, I use as eigenvalues the eigenvalues of the degrees of freedom with few lengths.
So again, I just blanked out in the first one.
I mean, what I would say, I don't know what I have some set of primitive operator on the inverse space that are the degrees of freedom.
The operators?
Yes.
The operators,
I analyze them because symmetry
Okay.
is 0, and so the value is described by the eigenvalues of
Yeah.
by the vector of but what change here in the case of entanglement value?
That's a very good question. I should definitely answer that now. So let's consider this Lagrangian. And we can ask, so we found that that the vacuum of this theory has some quirky features, right? If you haven't seen ChernSimons theory before, you might have never seen something like that. Okay? And you can ask, how do I see that there is such a long-range interactions between probe particles? That means that something is going on in the vacuum. But can you measure it by any local experiment? And the answer is clearly no, because to measure it, you have to do this funny Aronoff-Bohm type experiments. So clearly, locally, there is nothing. If you want to be mathematically precise, locally, you can set the gauge field to 0 at almost every point, except for one branch cut. But to measure where this branch cut is, you have to do a loop. And how do you see it mathematically? What are the gauge invariant operators in this theory? This is gauge invariant, right? This is gauge invariant, and so on. There are many gauge invariant operators. But what is the equation of motion of A in the absence of sources? It says that F is 0. So in this theory, there are no gauge invariant local operators. It's just, there is nothing even local that you can try to measure. You can ask, what about monopole operators? Yesterday we spent a huge amount of time. I tried to convince you that there are some local operators M, which are not written easily using A, but they nevertheless exist. So maybe they exist. And the answer, which I am not going to explain, is that they actually also vanish in this theory. So this theory has no local operators whatsoever. You cannot make any local measurement in this theory. Everything is about global things. Okay? So the operator algebra is vanishing in this theory. There is only one operator, which is the unit operator. That's the only thing you can measure. I want to mention one last thing before we finish. That's a very important historical fact, which is the case of k equals 1. And we're going to use this case tomorrow. That's why I'm going to mention it. K equals 1 is a very interesting and somewhat subtle special case, because in this case there is only one enyon. In this case, there is only one non-trivial enyon, which is, so there is q equals 0 and there is q equals 1. Remember that q is defined mod k. This is just trivial. This is the unit enyon. That doesn't have any Aronoff-Bohm phases. It's a trivial enyon. But this one has spin 1/2. So it's a somewhat degenerate special case where all the spins are either 1 or 1/2. There are no actual fractional spins for k equals 1. And spin 1/2 is a little bit like a fermion, right? A fermion has spin 1/2. So tomorrow we'll see in what sense this is true. Tomorrow we'll see that the dynamics of ChernSimons theory at level 1 with symmetric fields is in fact dual to a fermion. So you can make bosons into fermions using ChernSimons fields. So this is boson, fermion, this is related duality. So if you take a boson, you add the ChernSimons level 1 term, it becomes a fermion. We'll see tomorrow exactly what is the statement. But you see it qualitatively already here, that there is some connection between bosons and fermions if the level is 1. That's comment number 1. Comment number 2 that you should know is that another special case that the condensed matter people absolutely love is k equals 3. That's the Laughlin wave function for the quantum Hall effect. So the quantum Hall effect has a famous phase in, sorry, what did I write? This is conductivity equals the third. So that's the Laughlin wave function with 3 quasi-particles. It's a famous state of the quantum Hall effect. And Laughlin wrote the wave function. So the quantum Hall effect is a system in which you naturally get at long distances a Chern-Simons theory. So you might have seen this picture of the quantum Hall effect, that there are some edge modes and there is some stuff inside. So inside there is the Chern-Simons theory at level 3 in the most famous case. Okay. So there is topological order in the quantum Hall effect at some filling fraction. So k equals 3 is their favorite example in condensed matter. Many other examples of Chern-Simons theories also arise in condensed matter, but tomorrow we'll talk about that. Any questions? Yeah.
Is this fact that you are spin 1/2 particles, even if you are just in gauge theory, related to the fact that you can have soft anomalies, or with this bosonic theory?
So again, I didn't understand the question.
You can change the statistics.
Yeah, you can change the statistics. Yeah.
Related to the fact that even if this is just a bosonic theory.
Right. You might start from something that looks like a bosonic theory, in the sense that the Lagrangian that you write has only gauge fields and scalar fields. But then because of this funny stuff, effectively you might end up with a theory that has fermions.
And the question was, is this related to the fact that one can have those?
No, this is not related, because the example that I gave you before, the Snell-VBS transition, that had no transmutation of the statistics. It was a truly bosonic system with no transmutation of the statistics. So it's not related. You can have genuine bosonic systems with anomalies. Any other questions? Okay. So I'll see you tomorrow. Wake up.